Hello there. Welcome to section 4.5, the dimension of a vector space. We're going to jump right in this section and talk about two theorems right off the bat. And you'll see that the first theorem generalizes a well-known result about vector space Rn. So here is the first theorem we'll discuss. It's theorem 9, and it says if a vector space V has this basis here, then any set in V containing more than n vectors must be linearly dependent. So this theorem implies that if a vector space V has this basis, then each linearly independent set has no more than n vectors. The next theorem that we'll talk about is theorem 10, and this says if a vector space V has a basis of n vectors, then every basis of V must consist of exactly n vectors. Now, if you're interested in this proof, you can see this proof on page 228. But this theorem really just ensures us that the following definition, the definition I'm about to show you, makes sense. So here is a set of definitions here. And we're talking about finite dimensional sets and then infinite dimensional sets. So we'll be asked to find the dimension of different sets, and the notation is like what I have circled here. The dimension of a zero vector space is 0, and it's defined to be 0. And you can go ahead and read through these. But specifically, the dimension of V is the number of vectors in a basis for V. If V is not spanned by a finite set, then V is said to be infinite dimensional. Here's a brief example, and it says the standard basis for R3 contains 3 vectors. So the dimension of R3 is 3. Furthermore, any basis for R3 must contain exactly 3 vectors. And then similarly, any basis for Rn has exactly n vectors. And this comes from that theorem 10. Well, let's look at a more concrete example. So here it says find the dimensions of the subspace H given here. Okay, so take a moment and see what this subspace is. And let's see what we can do with it. Now, H is the set of all linear combinations of the following vectors. So V1 is all the coefficients of A. So 1, 5, 0, 0. V2 is all the coefficients of B. So -3, 0, 1, 0. Oops, V2. V3. Let that be all the coefficients of C. So 6, 0, -2, and 0. And finally, V4 is going to be the coefficients of D. So 0, 4, -1, and 5. Okay, so this subspace is the set of all these different linear combinations. So what we want to do now from this is we want to make some observations. Okay, so the first thing that we want to address is that V1 is not equal to 0. Okay, we don't have a 0 vector here. Okay, so V1 not equal to 0. the next thing you want to do is see if any of these vectors are multiples of other vectors. Well, looking at this, V2 is not a multiple of V1. However, V3 is a multiple of V2. Okay, so that's important. So let's see, V3 is a multiple of V2. Okay, well, by the spanning set theorem in the section we covered previously, so in section 4.3, the spanning set theorem said we can discard V3 and still have a set that spans H. So from this, we are going to discard V3. Okay, again, because we will still have a set that spans H. Okay, then we can go on and then look at V4. V4 is not a linear combination of V1 and V2. So we can draw some conclusions here. So V1, V2, V3 has been omitted, and V4 is a linearly independent set. Let's just say is linearly independent by, this is by theorem 4 in section 4.3. So because this is a linearly independent set, then and is, I don't know why I'm so sloppy today, and is a basis for H. So we can conclude that the dimension of H is 3. And that is ultimately what we wanted. Not so bad. This slide here, I just kind of wanted to mention the different subspaces for R3 depending on the dimension. A zero-dimensional subspace is just the zero subspace. A one-dimensional subspace of R3 is just this line right here passing through the origin. And then finally, a two-dimensional subspace of R3 is a plane passing through the origin. On page 229, it also talks about three-dimensional subspaces, and the very last part of your homework talks about that, so you might want to take a look at this page. Okay, so yet another theorem here. It says H is a subspace of a finite dimensional vector V. Any linearly independent set H can be expanded if necessary to a basis of H where the dimension of H is less than or equal to the dimension of V. Another theorem, this is referred to as the basis theorem. This is important in applied problems where linear independence is easier to verify than spanning. So it says that V is a p-dimensional vector space, and p is greater than or equal to 1. Any linearly independent set of exactly p elements in V is a basis for V. It goes on to say that any set of exactly p elements that spans V is a basis for V. The dimensions of null of A and column of A, you will see this. It's pretty straightforward and easy to evaluate these. When we want to find the dimension of null of A, that is the number of free variables in the equation AX equals 0, whereas the dimension of the column of A is column space of A is the number of pivot columns in A. So if we look at this example that we have here, we have this matrix that has been row reduced. And if we want to find the dimension of null of A and the dimension of column of A, what I would recommend doing is identifying the free variables and the pivot columns. If you look at this, these here are my pivot columns, which will tell us the dimension of column A. And if you look at the columns of the free variables, that tells us the dimension of null of A. So here is an example where this matrix is not row reduced. So what we want to do in order to be able to find the dimensions of the null space and column space, we will want to reduce the augmented matrix A0. And if we reduce that to echelon form, we can identify the pivots and the free columns and then ultimately find the dimensions. So remember, you'll want that 0 column there. And if you row reduce this, you end up with the following. And you are welcome to use a calculator or website to do this. Okay, so from here we can identify our pivots. There are 2 of them. Remember, the number of pivots tells us the dimension of column A. So the dimension of column A is 2. Then we want to find the number of free variables that will occur in these columns. This column here we don't care about just because that's a 0 vector. So these are the 3 free variables. And so that tells us the dimension of null of A is 3. Because 3 free variables. Wow, that was a fast one. Enjoy.